Hi there, and welcome back. We're going to look at another trigonometric graph. This time we're looking at the secant function, and we're going to take a step-by-step look at how different transformations applied to the equation will change the graph. Okay, so the first thing we'll do, I'm going to multiply secant by a number. In fact, this is the next graph I want to do. So I'm going to do 3 secant x. So changing the equation, I didn't change the graph yet. So think about what happens when you multiply by 3. Everything should stretch vertically by a factor of 3. So once I put the 3 here, notice that that has now changed where my minimum and maximum points are. So if I take the 3 away, notice that this minimum here is at 1. And this relative max here is at -1. In fact, all of them are there, and there's another 1. So then as soon as I apply a 3, they compress upwards. I should say they stretch upwards. And now my relative mins are at 3, and my relative maxes are at -3. Okay. So those are my relative minimum maximum values there. And notice, of course, that the graph overall just seems to have stretched vertically in both directions. The part above the x-axis got pulled upward. The part below the x-axis got pulled downward. Okay, so now what I'm going to do is I'm going to change the x to 2x. And remember what changes to the angle do? Those change the period when you're multiplying by a number. So notice that the period of the basic secant graph is 2 pi. So when you put a 2 in front of x, that should change the period to 2 pi over 2, which is pi. So let's take a moment and look at that. And yes, as we can see, let's look at 2 consecutive maximum points. We have one maximum point at pi over 2. The next one is at 3 pi over 2. That is a horizontal distance of pi. 2 minimums in a row are at 0 and pi. X equals 0 and pi. So yes, the period did indeed shrink. Okay, and that's because the number we multiplied by x is greater than 1. That's a horizontal compression. Okay, and then naturally, if I decide I want to add, let's say I want to add 4 to the equation or to the function, that should mean that all the points that you see should shift upward 4 units. So let's take a look at what happens if that's correct. Looks to be correct. Okay, I'm actually going to move that equation slightly so it's out of the way of the graph. There we go. So as we can see, the graph has shifted up 4 units. Now this minimum point is way up here at 0.7, the relative minimum, and these relative maximums are at 1. So everything just shifted up 4 units. And that is explaining basically step by step what happens to the secant. One thing to notice also, remember that with a sine or cosine curve, that multiplier in front of the secant was considered an amplitude if it was positive. I'm sorry, in front of the sine or cosine was considered an amplitude. With secants and cosecants and tangents and cotangents, those graphs already are unbounded, so there is no concept of amplitude, but that 3 is basically just a stretch factor, okay? And had that been a -3, it would have also reflected around the x-axis as well. So the number that the coefficient of secant, cosecant, cotangent, or tangent is strictly a stretch factor. It is not to be interpreted as an amplitude because, again, amplitude refers to a constrained wave where it only can go so high and so low. So I hope you enjoyed that little demonstration of what happens when you take a basic secant graph and apply some transformations to it.